close out today, let's talk about this interesting question of whether or not a short or compressed bit stream is also a comprehensible bit stream. So remember much earlier, we talked about our dream of comprehensible compression. We take an image, we feed it to a comprehensible compression algorithm, and it gives back a readable file that we can look at and try and learn something from. So Scott Aronson's quote earlier, which talks about the amazing powers we would be granted by being able to compress using our P equals NP based solver, he made the implicit conjecture that a short program will be comprehensible. Now that's feasible to me. It seems like, yes, a short program will probably exhibit hierarchy and structure and might look like hugplant.java, but there's reasons why I think maybe it wouldn't be. So I'll give you another example of this idea of compression, why it's so powerful. So Scott conjectures that if we fed in a bunch of useful information about the stock market, this is just a cartoon, not quite right, but say we give every business report or yearly report or whatever else, along with all the stock market data ever, and we feed it to our comprehensible compression algorithm, we would get back something that's basically an economy simulator. And we could then open up that Java file, and we could read the source code and hopefully understand how the world works. Similar to if we had this plant. If we fed it into this comprehensible compressor, we'd be able to see, draw rectangle and pick color and so forth. We would get similar ideas here. So this Java program would be a simulator that's able to give back all the market data, and we could read it and understand, presumably, something. Now, as I'd said a while ago, while it does seem feasible that a short compressed program would also be comprehensible, it might not be. So earlier, we said that compressibility was a rare thing, that most bit streams are not compressible. But it is the case that short programs can produce surprisingly complex output. Hugplant, for example, but it goes a lot deeper. So for example, my classic example is a fractal. So in the 1970s, Mandelbrot, very famous guy, he created demonstrations that very short programs could give extremely complex visual patterns. So this is not a real cauliflower, but it does somewhat resemble this actual cauliflower here. This is a specific variety of cauliflower that is this fractal structure. And so this implies that, to me, that biological processes exploit these same ideas, these little subtle, tiny programs that can actually give rise to very complex patterns. So that is, a short sequence of DNA in this cauliflower is able to give rise to this nice 3D structure in the same way that the program that generated this right here is very short. Okay, so we haven't talked about fractals in this class, but the basic idea is that the code for this thing, despite its complexity and beauty, is extremely short. So let's take another example of a fractal. This is something known as a Mandelbrot set. It is a very, very rich data structure, piece of information. You can even zoom in and see tons and tons of ultra fine detail. So let's say we feed this to our bounded space-time compression algorithm. The answer is, would it be comprehensible? Well, the output, if it's actually really good, would maybe look something like this. So this is, I've taken it from Rosetta Code, in which various folks have implemented different data structures and algorithms, and one of them is the Mandelbrot algorithm. So if we look at this code, we would see that the actual code needed to generate this extremely complex structure is actually very simple. It's only so many lines of code, and there's not a lot going on here. So what we have is only a very basic set of rules, but we get back what is a highly complex object. And so you might argue that we don't actually gain much insight by looking at this, that the complexity is sort of a mathematical property of the universe, and then just looking at this, it's not telling us something fundamental about the Mandelbrot set that's useful to us as human beings, but instead is reflective of the fact that very complex patterns can appear from simple rules. But hey, I'm not the complexity theorist. I don't want to pick apart Scott's argument too much, but I do want to raise this issue that simplicity is not necessarily comprehensibility. All right. So just in this lecture, I figured I'd mention a really cute application of this idea of simple rules giving complex patterns. So I'd say that while fractals are cool, if you've never seen them, I think fractals, or the ideas of fractals applied to sound, are much more interesting. So let me just show you a little demo here. So this is an adaptation I made of someone else's work. It's a shorter version. And this is going to be a number of really short programs that generate really complex output. So for example, here is a program. You see it's very short, but if you listen to the sound that results, it's actually pretty interesting. So that was it. That tiny program was able to make that kind of rich sound. Here's another example. So that building beat you hear is literally just this exact program. Very short. It's only a few lines of code. Actually, it's only one line of code. Now it's got a lot of symbols you don't know, and that's fine. If you take 61C, you'll learn about what these things are, but that's it. That's all there is. You feed this sequence of bits into an interpreter, and you get back the sound, along with some function calls not shown. Okay, so this one's a little richer. Nice little melody. Okay, this one I think is pretty nice. So again, this very short program, it's got 6689 in quotes for some reason. Okay, we run it. And the last one, which I find really, really impressive, is it's a longer program, but still quite short. So you can imagine that if you were to take that song and run it through a compressor and you get back this information, I don't know that that's useful at all, but it is fascinating to me that such short programs can produce such complex behavior. So as one last thing you might want to try out, if you'd like, there was a lab in Spring 18 where you could build your own fractal sound generator. You can click this link and you could do that in Java. So if you want, you can read through this spec and do everything from scratch, or if you'd like, you can just play around with this JavaScript sound generator that I've created. And just to give you a sense of what this thing is capable of, so that maybe you'll play around with it, the default sound you get out of it, hopefully this isn't too loud. Okay, so that's the default program, plays a sine wave. But if I take, for example, I replace that code here, and I do the following, I get back. And I'm not going to talk about why any of this works, but the point is that even really short programs can result in very complex outputs. And that's kind of the heart of compression. All right, so I hope you found that really cool, and that wraps up today. If you want to see even more interesting inputs you can put in that JavaScript program, then you can try out these slides for my generative art class that I taught also. So that's it for today. I hope you found it fun, and yeah, that's the technical content of the course. We'll wrap up next time and call it a day.